This is a DC motor speed controller using a power op amp. We have a potentiometer with a dial on it, which serves as our input. The potentiometer is read by a PIC microcontroller, which reads the analog voltage and converts it to a digital value. The digital value is transferred to an external D to A converter, which outputs an analog voltage, which is the input to a power op amp circuit. It's configured as a non-inverting amplifier. And finally, that sends a voltage to a DC motor, which is coupled to a planetary gear drive. The power op amp can be driven by a single polarity voltage source, but in this case we are using a plus and minus voltage source. We currently have positive 9 volts coming in, a negative 9 volts coming in, and a ground reference. We're using a voltage regulator to drop the 9 volts down to 5 volts to power all of the digital electronics. So when we power it up, we have an LED blinking that indicates that the PIC is running. As we turn the potentiometer, the speed of the motor will gradually increase at a speed proportional to the potentiometer displacement. So here it's turning at a very slow speed. We can increase the speed slowly with the potentiometer. And the more we turn, the faster the motor turns. So again, we're outputting a higher and higher voltage to the motor. At this setting, we're outputting about 5 volts to the motor. It's turning fairly quickly, even with the 18:1 speed reduction. And the power amp circuit is drawing about 120 milliamps. And we can slow the motor down again by turning the potentiometer in the other direction. Down to 0. There's a slight hesitation in between speed changes because we have a slight delay on the PIC between updates. So every time the LED blinks, there's a small pause before it updates the new voltage. Because the current demand of the motor is not very large, we can use 2 9-volt batteries to power the circuit and have ample supply for a fairly long period. The 2 batteries are wired in series, and the center tap serves as the ground reference. So relative to that, we do have a positive 9 volts on the positive side and a negative 9 volts on the negative side of that center tap. So this is providing the same voltage inputs as the power supply. So even at the highest voltage and highest speed, the batteries provide ample current. Here's a close-up of the circuitry. We have a potentiometer wired as a voltage divider. The voltage input from the wiper is input to an A to D input of a PIC 16F88. The PIC converts this analog value to an 8-bit digital value, which is output through port B to an external D to A converter. This is a TI TLC 7524. The D to A converter outputs its analog voltage to a power op amp circuit that's configured as a non-inverting amplifier. So we have an input resistance and a feedback resistance. The feedback resistor is 10K, the input resistor is 1K, providing a total gain of 1.1. The power op amp is a TI OPA 547. The analog output from the op amp circuit goes directly to the motor. And again, we have a 7805 voltage regulator that regulates the positive 9 volt input down to 5 volts to power our electronics. Both the regulator and the power op amp have heat sinks attached to them. It's aluminum fins that help dissipate the heat that these components generate. Now this circuit is a bit of overkill because we could attach the potentiometer directly to the power op amp, avoiding the A to D conversion and the D to A conversion. We just did it this way to show how you can assemble all these components and to show how you can introduce a microcontroller into the loop that would allow you to write some control software to do more sophisticated control of the motor.